Most of these properties can be determined using just two types of grains: the lowest interference colour grain, preferably dark first order grey, and the maximum interference colour grain. Not every property may be relevant to a particular mineral. Thus, if there's no crystal form, we cannot determine sign of elongation or draw an orientation sketch. After determining these properties, we normally try to identify the mineral. This is a worked example showing how to determine all the properties we've learned about for an unknown mineral in thin section. Typical grains of this mineral are circled. First, check the general features of the mineral so that we can distinguish it from other minerals elsewhere in the slide. Close the diaphragm to check relief, rotate the stage to check pleochroism, and cross the polars. Now scan the slide and note any other features. Search carefully for the lowest interference colour grain to get a useful interference figure. For each field of view, rotate the stage in plain light and cross polars. Note the strong pleochroism and the grain shapes varying from equant to prismatic. Here's a suitable grain. Check in plain polarised light that it is the right mineral. Rotate in plain light and the colour should not change, and it is the O colour that we're looking at here. Put the grain at the crosswire intersection and select high magnification and refocus. Rotate the stage to check that the grain stays at the crosswire intersection. If not, adjust the centering. Swing in the auxiliary condenser and open the diaphragm. Cross the polars and insert the Bertrand lens, and here's the result. Rotate to check that the uniaxial cross remains intact, that is, that it is not biaxial. Use the plate to determine the optic sign. There's a fall in the northeast quadrant, so the mineral is uniaxial negative. Now scan the slide for the maximum interference colour grain, also a crucial grain to find as it yields several important properties. The maximum interference colour is around second order yellow. So with that maximum interference colour grain, again, second order yellow, a retardation of about 950 nanometres, find this band on the interference colour chart and find where this band intersects the thin section thickness line, 30 micrometres, and read off the birefringence, about 0.03. Rotate the maximum interference colour grain in plain polarised light to see the two limiting colours, dark bluish green and pale brownish. The lowest interference colour grain we used for an interference figure indicated that O is the dark colour. So that's the O colour. And that's the E colour. Thus, the pleochroic formula is E equals pale pinkish brown, O equals very dark bluish green. The absorption scheme is O much greater than E. We can check the pleochroic formula using another method. Rotate the E vibration direction 45 degrees anti-clockwise and add the plate. The interference colours fall, so E is fast. This fits the negative optic sign. Check by rotating 90 degrees to see the opposite effect. And that's the rise. So it was a fall in the first position. So this confirms the pleochroic formula. That's the E colour, the fast ray, and that's the O colour, the slow ray. For this property, find a long, well-formed prism, preferably with maximum interference colours, and rotate under cross polars. Note that it goes to extinction when it is parallel to the cross wires. That is, it's a case of parallel extinction. This property is relevant as the mineral has parallel extinction. Rotate the long axis northeast-southwest, add the plate, and it seems to fall, first order red going to black. Rotate 90 degrees to see the opposite effect, a rise. So it must have been a fall in the first position. Therefore, the mineral is length fast or has negative elongation. That is, the fast ray vibrates parallel to the C-axis. The parallel extinction shows the vibration directions are parallel and perpendicular to the length of the prism. The negative sign of elongation and the negative optic sign show that the E vibration direction is parallel to the length and the O vibration direction is normal to the length. So we can now draw a two-dimensional sketch of this prism showing the crystallographic features and the main optical directions. The crystallographic features include the prism outline and the C-axis, and the optical directions involve the E and O vibration directions. For these properties, examine a variety of grains ranging from equant to prismatic. Check for parallel cleavage traces in one or more directions, and for twinning, cross the polars and rotate the stage. No cleavage is present, only some irregular fractures, and we cannot see twinning either. We estimate the average refractive index, not the individual values of omega and epsilon. Any grain can be used. Close the diaphragm. Estimate delta N from the relief. It's moderate, so delta N is about 0.1. Determine the sign of relief relative to quartz, Ri 1.55. Racking up, the Becky line moves in. Racking down, the Becky line moves out. So Ri is greater than 1.55, and the Ri of the mineral is 1.55 plus 0.1, or about 1.65. We can also use the glue, refractive index about 1.54, as a reference substance. Find the grain of the unknown mineral in contact with the glue on the edge of the slide. In plain polarized light, close the diaphragm, raise the focus, and the Becky line moves into the mineral, so it has positive relief. That is, a greater refractive index than the glue. And that's the same result as we got when comparing the unknown refractive index with quartz. After determining the properties, we would normally use identification tables or reference data to identify the mineral. Not all these properties are equally useful for identification of the mineral. The diagnostic properties seem to be uniaxial, colour and extreme pleochroism, crystal form and length fast, and birefringence about 0.03. The mineral is tourmaline.